Welcome to GER Hub Mathematics and Statistics lessons. Today I'm going to be talking about set theory. Okay? So, let's see, where do we begin? Now, in this video, I want to talk about set theory, starting with the definition of set theory and also explain certain important things you need to know about set theory. So this will be a part 1 video to set theory. So let's see. Now, the question is, what is a set? What is a set? So let's start with explaining that. A set is a collection. A set is a collection of well-defined objects. A set is a collection of well-defined objects. Now, what does that mean? So, let's underline the word collection and let's also underline the word well-defined. So, by collection, what we mean? So, collection simply means or refers to a group of items. Okay, so any group of items would make a collection. Any group at all of items will make a collection. So what it means, the implication of this is that a set goes beyond just being a collection. Now, let us look at the word well-defined to explain it as used in the definition. So the word well-defined and the word collection are two key words in this definition that will help us in understanding what a set is. So the word well-defined means that the elements or objects of the set must have at least one property or feature common to them. So a set is a collection of well-defined objects. So if we want to look at the word collection simply means that we are referring to a group of items. But the word well-defined means that this group of items we are referring to must have one or more. That's what the word at least means. At least one means one or more property or feature common to them. So if a set has a collection that is well-defined, or if in a set we have elements rather that are well-defined, it means these elements or objects have properties, at least one, common to all of them. So what is called a set is a collection, and not just any collection, but a collection that has elements that are well defined. And again, if objects or elements in the set are well defined, it means that those objects or elements have one or more properties that connect all of them. So what is the first implication of this? What does this definition mean? What does the definition mean? The definition means, by implication, that not all collections are sets. So the first implication is that not all collections are sets. Implication number 2 is that every set is necessarily a collection. Okay, so every set is a collection. That is what this definition means, but not all collections are sets. So let's see what that means. Okay, so I'm going to put up a collection. To start with, let's put up a collection like this. let's put up a collection like this. There is kettle, there is a pen, there is a book, and there is a car. This makes a collection. A collection in the sense that it contains kettle, an object, pen, an object, book, an object, and car, an object. But the question is this collection a set? The answer is no. This collection is not a set. And why is that so? It is not a set because the elements in this set or the objects in this set are not well defined. Why are they not well defined? It is simply because there is nothing which connects a kettle to a pen, nothing that connects a pen to a car, although there is something that connects a pen to a book. Both of them are writing materials. But the question is, what connects a car to a kettle? What connects a car to a pen? What connects a car to a book? What connects a kettle to a book? So there is not one property that binds all of them. So this collection, if you ask, is this collection a set? This collection is just an ordinary collection. It is not a set. For this collection to be a set, it means the objects in this collection must be well defined. And for objects in the collection to be well defined, it means they must have at least one property that binds them. And in this case, there is no property. So what if I had put a collection like this? Kettle, spoon, a cooker, and then a pot. This collection, is it a set? The answer is yes, it is a set. So why is this collection a set? It is simply because there is at least one property binding the elements in the set. Kettle has a relationship with spoon, spoon has a relationship with kettle, kettle has a relationship with cooker, cooker has a relationship with kettle, kettle has a relationship with pot, pot has a relationship with kettle, spoon has a relationship with pot, pot has a relationship with cooker. All of them are things or objects we find in the kitchen. They are things we use as cooking utensils, or they are things found in the kitchen. So they have at least one property that binds them. So this is a set. This is not a set. It is just a collection. So in addition to this being a collection, it is a set because the elements in the set are well defined. Now, if we move over to the next one I want to give, I'm going to put here apple, I'm going to put here pen, and I'm going to put here a car, and I'm going to put here let's say a book. Now this collection, is it a set? The answer is no. Why is it not a set? The elements do not have at least one property that binds all of them. Whereas car and book have a relationship, pen and apple have no relationship. So this is a fruit, this is a writing material or a writing utensil or a writing object. This is a car which has no relationship with the pen. So apple, pen, car and book have nothing in common. Two or three of them may have a thing in common, but all of them together do not have one thing in common. So no, this is not a set. It is just a mere collection. Okay? Now that being said, I hope you understand the difference between a collection and a set. A collection is just a group of items, but a set, in addition to being a collection, has elements that are well defined. Well defined means that the set has elements having a property common to all of them, a property or more common to all of them. Now, the next thing I want to explain in this video is a confusion. I want to explain a confusion with the definition of set. Okay? I want to explain a usual confusion with the definition of set. So, let me write it as what is not a set. What is not a set? So, there is a definition going around that does not describe mathematically what we define to be a set. What is that definition? That definition goes this way. A set is a well-defined collection. A well-defined collection of objects. Now, please take note, this definition of a set is wrong. Why is this definition wrong? In defining a set, the emphasis of being well defined is not placed on the collection, it is placed on the object. So it is not the collection that has to be well defined, it is the objects in the set that have to be well defined. Okay? So the definition here, a set is a well defined collection of objects, is wrong because the well defined property is not on the collection, it is rather on the object. So what should be well defined are the objects in the set, not the collection. Okay? So that is why that set is, this definition of set is wrong. So please take note. What is a set? A set is a collection of well-defined objects. A set is not a well-defined collection of objects. So students often make the mistake of confusing these definitions. The one that is correct is the first one. A set is a collection of well-defined objects. And that is because the property of well-defined should be on the objects, not the collection. Okay? So let's now move to the next thing I want to discuss in this video. So what else do I want to tell you in this video as an introductory class on set theory? The next thing I want to tell you in this video on set theory is that sets, in set theory, we use uppercase letters. Uppercase letters are used to denote sets. Okay, so we use uppercase letters in set theory to denote sets. So any of A, uppercase B, C, D, E, F, and so on can be used to denote a set. Now, while we use uppercase letters to denote sets, we use corresponding, most times, corresponding lowercase letters to denote the objects or the elements in a set. Full stop. Okay? So if we use capital A, B, E, M, C, D, E, and F, and so on, or uppercase A, B, C, D, E, and F to represent the set itself, then we would likely use small a or lowercase a, lowercase b, lowercase c, lowercase d, e, f, and so on to represent the elements in the set. So what I want you to know in this video, in addition to the definition of a set, is that uppercase letters are usually used to represent a set, while lowercase letters are used to represent the elements in a set. Now let me clear the air on this. This is not a strict rule, okay? You can use any other symbol to denote a set, or in particular your set, provided you tell us when using any other symbol that this represents a set. So if you are to use any other thing to represent a set other than uppercase letters, or you have to use any other symbol to represent a set, or to represent the elements of a set other than lowercase letters, then you must specify in that write-up that such represents the the set itself, the symbol you have used represents the set itself, or the symbol you are using represents the elements. So otherwise, uppercase letters should represent set, while corresponding lowercase letters should represent the elements in a set. So that concludes the second thing I want to describe. So if there is a set A, then the elements in that set A should be small a. If there is a set B, capital B, the elements in that set should be represented with lowercase b, okay? So, and so on. Let's go to the third thing I want to tell you in this video. So the third thing I want to make mention of in this video is about the description of a set. How do we describe a set? I'm going to mention ways we describe a set, but I'm not going to explain in detail in this video. That will be saved for the next video, okay? So I'm going to call it description of a set. Description of a set. Okay? So sets can be described. Sets can be described using any of the following means. Sets can be described using any of the following means. Number one, sets can be described using what is called the method of listing. The method of listing. So we can use a method called the method of listing to describe a set. This method is also called roster method. Roster method. Okay? So the method of listing is also called roster method. There is a second method called the method of set properties. The method of set properties. Okay? I'm going to describe all these methods in my next video on set theory. So the method of listing, also known as roster method, is a method of describing a set. The second method is the method of set properties. The third method for describing a set is the method of set builders. Set builders. Or it is called set builder notation. Set builder notation. Or may be called set theoretic notation. Set theoretic notation. Okay? So, there are three ways I've listed here so far. 1, 2, and 3. The first method of describing a set is the method of listing, also called the roster method. The second method of describing a set is called this method of set properties. The third method of describing a set is a method called the method of set builders, or the method of set builder notation, or the method of set theoretic notation. Now, I want to mention that these three methods are theoretical methods. They are all theoretical methods of describing a set. These three methods are theoretical methods of describing a set. Now, why am I putting them together as theoretical methods of describing a set? It is simply because there is, for describing a set, a fourth method, and that method is called the method of Venn diagrams. The method of Venn diagrams. Okay, so there are 4 methods available for describing a set. The first method is the method of listing, also called roster method. The second method is the method of set properties. The third method is the method called set builders, or set builder notation, or simply put, set theoretic notation. And the fourth method is the method of the Venn diagram. Okay, the method of the Venn diagram. So I am going to be explaining in my next video description of sets, or description of a set. So I'm going to be explaining in detail how these methods are used, these 4 methods are used, and what they mean. Okay, so let's move on to the next thing I want to describe. I want to describe 2 classes of sets. So classes of sets. I want to describe classes of sets. So sets may be finite or infinite. So a set may be finite or infinite. Okay, so the question is, when is a set finite? So a set is finite. A set is finite when it contains countable and exhaustible number of elements. A set is finite when it contains countable and exhaustible number of elements. So sets are finite when they contain countable and exhaustible number of elements. What does that mean? It means that sets are said to be finite if the number of elements in them can be counted and one can finish the counting. So that is what it means. A set is finite when the number of elements in that set can be counted and we can complete the counting. Now take note of one thing. We use in set theory, we use what is called a curly brace. So elements of a set are put in curly brace. Okay? And how does a curly brace look like? A curly brace is a bracket that looks like this. So if you want to put elements or describe elements of a set, you put them in a curly brace, and this is a description of a curly brace. So let us now see, still on finite sets. Now another thing I want to tell you is, because a finite set is a set that contains elements that are countable and exhaustible, meaning that elements that are countable, elements we can count and also finish the counting. It means that finite sets could be large or small. Okay? Now, remember, finite sets are sets that are countable and exhaustible. Now, they could be large, they could be small. And the elements of a set are put in what is called a curly brace, which I described earlier on. A bracket that looks like this is called a curly brace, okay? Now, since finite sets are sets that are countable, that contain elements that are countable and exhaustible, how do we describe small finite sets and how do we describe large finite sets? So, an example of a finite set could be 1, 2, 3. A set that contains 3 elements, 1, 2, and 3. It is also a set that contains O, J, E, F. Just 4 objects. Notice that this is a finite set because I can count the number of elements and I can finish the counting. This is also a finite set because I can count the number of elements and can finish the counting. This is also a countable set. 1, 2, 3, 4, 5, 6. Now note, these 3 sets are small sets. Why? They contain countable and exhaustible number of elements which are small enough that one can actually write out the complete set of elements in a brace. But when they become large, when you want to describe a large finite set, take note, you would need what is called an ellipsis. You will need what is called an ellipsis. An ellipsis symbol is what you would need. It is a 3-dot symbol showing us that the counting or the listing of items continue up to a certain point. So if I want to count a large finite set or even a small finite set that I can't describe because of space, the number of elements, I would do something like this. So let's say I was to count 1, 2, 3 into my set up to 100. Because the space available will not be sufficient to describe by counting 1, 2, 3 to 100. I will put an ellipsis, that is the 3 dots, put a comma, and then put the final element in that set, being 100. This ellipsis shows that the counting continues after 3 down to the last element, which is 100. and the 1, 2, 3, note that I have taken the first 3 elements before putting the ellipses. By convention, we suggest you put the first 3 elements, showing us the pattern the elements in that set follow, put the ellipses, and then write the last element in the set. So if I wanted to describe a set that contained elements ranging from 15 down to 100 or 1000, I'll put 15, 16, 17 ellipses up to 1000. Now, I am describing these ones as large sets just to show you what should be done when describing a finite set that is bigger than your space available for describing it. So if you want to describe a large finite set, take note, finite sets are countable and exhaustible. So why are they countable? It means the number of elements in them can be identified or listed or counted. But why are they exhaustible? They are exhaustible because you can finish the counting. Note, this set that is large, up to 100, we can actually finish the counting. That's why we know that the last element is 100. Same also goes for 1000, okay? Now, moving on from there, let us go to infinite sets. Infinite sets. So, infinite sets are sets that are countable but inexhaustible. Now, students often make the mistake of thinking that once a set is infinite rather, it is not countable. That is, the number of elements in the set cannot be counted. No, counting should not be seen in a sense of finishing the counting. So, infinite sets do not actually refer to sets that cannot be counted. They refer to sets whose elements can be counted, only that the number of elements in that set you cannot finish counting. So, infinite sets are sets that are countable but inexhaustible. So, they could also, they are generally large. So, I'm going to write here, infinite sets are large sets. Infinite sets are large sets. Now, the same way we use the ellipses to describe large finite sets, we also use the ellipses to describe infinite sets. How do we do that? If, for example, I wanted to write out the elements of the natural number system, 1, 2, beginning from 1, 1, 2, 3, down to the last element, because the number of elements in the natural number system cannot be exhausted. You can't tell where the natural number elements, all the natural numbers end. Because you cannot tell, it means you can actually count, but you cannot finish the counting. So what do? We count the first 3 and then put ellipses and close bracket. So examples of infinite sets are natural number system. The natural number system is an example of an infinite set. The natural number system. Take note, we use this symbol to denote the set of natural numbers. So the set of natural numbers is an example of an infinite set. The set of integers denoted with this type of Z, or sometimes it can be denoted with this type of I. This is also an infinite set, because you can actually count the first set of integers, but you cannot count or exhaust all of them. Rather, you cannot exhaust all the integers known to man. So also goes for the set of rational and irrational numbers, and irrational numbers. The set of all rational numbers and the set of all irrational numbers are also infinite sets. So this set we usually would denote with this. You may denote this with this type of F, okay? So if we use this type of F to denote the irrational number system, then this set is infinite. Why is the set of all natural numbers infinite? Why is the set of all integers, rational numbers, and irrational numbers infinite? It is because we can actually count some of their elements but cannot count all of them. The set of all real numbers, denoted by this type of R, is also infinite. Okay? So infinite sets are sets that are countable but inexhaustible. So for us to represent them, we use ellipses. If I want to represent another infinite set, I could start with 2, 4, 6, 8, 10, 12, and so on. It goes on. But usually I would have used just the 3 elements and then put an ellipsis to show the set of even numbers extracted from the set of natural numbers, and that is also infinite. Okay, so finite sets are sets that are countable and exhaustible. Infinite sets are sets that are countable but inexhaustible. Please like our video, share our video, and most importantly, subscribe to our YouTube channel for more videos on mathematics, statistics, and even research. And I'll see you all in a bit. Thank you.